Oh, wow. Look at that. There is NCEAS is live. All right. I'll just give it one more minute. Okay. Can everybody hear me okay? Cool. All right. So there are a few questions that were asked that I really need to give more attention to and update the species lab materials. I am lagging and I will do that by tomorrow for sure. The species lab is being pushed back to when this community lab is due, so next Wednesday. And then we'll push the community lab back too. Yeah. So I want to be sure to give enough attention to the questions, which were excellent, and you allow you guys to have time to also write up the lab with a few more instructions, and yeah, hopefully this communities lab isn't too hard. It's actually just mostly running the code and with a few questions in there for you to kind of ascertain how these things work, and just tweaking a few parameters to rerun. So I will go ahead and start in on this clustering lab. And really, this communities lab the idea was to start off with supervised learning, in that we have the why, the response that we fit the models to in that first module of species distribution modeling, where we have data that we're feeding into the model about where we see presence versus absence. And then we're trying to get the model to differentiate between those two with an environmental relationship. So that's supervised learning, when the response is part of the fitting of the model. Now, unsupervised learning, you'll recall, it is not, we don't have the response term in it. So if we look at this, remember this was the slide from the first lecture about unsupervised learning. In this case, we might think of like a cluster. And maybe this is some environmental gradient, and we see species cohabitating. And I was involved in for instance, a cetacean community, whales and dolphin community environmental analysis that I had a slide on in that first lecture too. And the idea is like just figuring out like, well, maybe there's some clusters, and this can get used for all kinds of reasons. It can get used to try to pre-process data, to look at similarity environmentally, to look at species composition, which you will do, and yeah, so we don't know what the clusters are, and we're having that technique help us determine them. So that's why it's unsupervised. The response is not labeled. And so clustering is one of the unsupervised techniques that we'll be learning, and that's what we're focusing on today. And then on on Monday, we'll look at ordination, which is about collapsing the axes. So you can have many data representative in single axes. But today we're going to talk about clustering. And this is from a review of clustering techniques. And we're not going to go over every single clustering technique. We're really just going to go over 3. One is this hierarchical approach, and the other is this partitional approach. And k-means is really what we're going to be using. So these are the most common techniques. And let's just look at this k-means clustering, which is definitely the common clustering technique. It's an algorithm that's heuristic, meaning there's not an absolute answer, and each time you run it could actually be different. So k is the initial means, or the number of clusters. And with k-means clustering, you actually have to specify, like, how many clusters do you want? And let's say this is our set of points. If we want 3 clusters, it's going to randomly identify 3 of those points, and then look for the nearest neighbor. Now, this nearest neighbor, you guys are going to create one of these too. It's called a Voronoi diagram. And that's just differentiating between these 3 centroids that are the circles, and finding the region that is the nearest region. So whatever other data points are within that region then get assigned to that centroid, because that becomes the nearest centroid. So all these in the light blue, all the points within the light blue polygon of that region then get assigned accordingly. And then what happens is that then the centroid of each of the clusters, so it becomes the new mean. So then the centroid can get jiggered to different places, and you're looking for what describes the least variation between these axes to achieve a cluster based on the number of clusters you want. So see this, there's more basically variation because the distance from the centroid to these points is then greater over here in this configuration than over here. So if you just get the distance, from here to here at these points, sum them up, this configuration you can see has less variation, less distance from centroid to other corresponding points, and that's what makes it the preferred cluster. So this tends to it gets run multiple iterations, and there's this example data set that comes preloaded in R. There's a bunch of them, but this is a common one. And actually, Alison Horst was involved in a penguins data set, which is like the analog. So iris is these different species of iris flowers and taking measurements from them. And if you just look at the scatter of points from the data set, then this is where those points fall. And it looks like, there's a cluster here, and then there's some stuff up here. And so this is sort of the naive view of the data. If you're just looking at these 2 variables, petal width and petal length, and each point then is an observation or a different measurements of a different flower. And so it looks like we've got these 2 clusters. But if we actually plot the data, we've got these 3 species. So now we can color code this, and you guys will do this in the lab with these 3 species. And they have a fairly clean clusters that you can kind of see. So then the question is, well, can we use this clustering technique with, say, 3 clusters and predict back what the species are. So we're not feeding the actual species data in, but we're kind of using it as a little check afterwards to see if it does a decent job kind of gathering the spread of these natural species traits. And yeah, what we see is that it looks pretty similar. So we've got, here's one cluster, that's pretty obvious. Here's another, but then where there's that liminal zone, there's actually, if you toggle back and forth, there's like this over this point right here. In the original, it's blue, it's Virginica, but it's understandable how it's green over here. So this is actually, if we're just looking at these 2D space, you remember we talked about recursive partitioning with the decision tree analysis. And this is kind of similar, except rather than dividing the variable space based on splits in the data, it's using a centroid approach. So it's creating, it's like this Voronoi diagram thing, and it's just based on a centroid, and we don't have the response data in the model that gets fitted there. So it's just based on a centroid. So that's unsupervised. But there is similarity to the decision tree stuff in kind of the abstract to what we were talking about. And you'll see more of these decision trees when we talk about hierarchical classification next. So yeah, and then you can actually, there's a little GG Voronoi, I gotta figure out how to say that word. Voronoi. If anybody else knows how to say it properly, feel free to chime in. But there's a little package that can help us draw these Voronoi regions that clearly describe what the nearest centroid would be. And so what you'll want to do with the lab is play around with changing the number of clusters with this little data set and just see how that tends to break up the space as you change the number of clusters, and see how that membership then varies too. Okay. Do we tell the model how many times to rerun itself to find the preferred clusters? So there are some default values, and in the way that I'm kind of borrowing from a few different texts with these labs to introduce you guys to these concepts, but the hands-on with machine learning talks about one of the, I'll click to that in a minute when I get through the slides, and we'll look at it has some nice informational tips that talk about the number of iterations to start with, and it says like 10 to 20 replicates to start is a good idea. So it also depends on maybe the data set. You can, with really big data sets, can become really slow to run these a number of instances. So maybe based on compute power, but there are some default terms, and one of them is how many replicates to first run. Okay, so how is this unsupervised learning if we know that why the species? Okay, so it is that this is just a sort of a demonstration use case. So the actual fitting of the model does not use the species information at all. So you can't see that here, but when we actually open up the lab, let me just go ahead and do that. And so this is you can load the data set just by saying data iris. And a lot of times you can even just use the iris with unquoted, and that's in R, that's lazy loaded. So it's in the background, even though it doesn't show up in the environment pane in RStudio. But when you do this, it actually says, okay, put that in the environment in RStudio explicitly so you can see it. And then you can get help on it, and that gives you the documentation. So this is the data, and all we're looking at is this petal length and petal width, and we're not actually using the species column. That's just a comparative thing. So here, if we plot this, the aesthetics for that plot are just petal length and petal width, and just a scatter plot, so G on point. And then this is actually plotting it with the species. But with the k-means, it's pretty simple. We just say, okay, k-means, and this is selecting just petal length and petal width. So species is not involved in this model output. It's just the k-means, and that's why it's unsupervised. And we're getting the clusters back with the y, in this case, an identification of which cluster each observation is a member of. And so we get these three, and then this is just comparing like with those cluster clusters. So these are arbitrary numbers, 1, 2, and 3. And how does that match? So in the table function, it tabulates the values, like how many setosas that have a value of 1 that in the cluster. So this is actually setosa was down here in that 1. So that we basically got perfect. That was a perfect match. Now we're not trying to, the clustering technique is kind of irrespective of the fact that we have a species label on these things. So that's just a little comparative thing for later. And later you'll see things get a lot more complicated when we look at like site composition and things. So this is just a little k-means cluster, and it happens to have a label that we can compare the cluster to. And you can see this Voronoi diagram. So this is just saying like, okay, so there was a cluster 2, and that matched up with 48, and cluster 3 matched up with 46 of Virginica. So these are different iris species. And then there was 2 and then 4 here that didn't neatly fall into those categories. So it's somewhere in that sort of liminal space that where the Voronoi shows up as this clean line, and that's where it's not as clean in the actual data. But this is this can be used to look at all kinds of membership and clustering, and maybe if you have a poor number of observations, you can look at similar species and then cluster them, maybe based on environment. So we'll get more into underlying variables and dealing with those next time. But then let's also talk about, and then some of the tuning part. So with this hierarchical clustering, I'm actually having you reference the text here from the hands-on machine learning with R. He did a pretty good job of explaining this part. There is a k-means clustering section, and in it he talks about this, a good rule for the number of random starts is 10 to 20. And that goes back to the other question about how much to iterate, how much to include there. Okay, so
and there's a question in the chat.
Is there another question, or maybe it's the Slack? how is this unsupervised learning if we know the Y species values going in? So is that, I think that's what I was trying to say about the fact that we don't use the Y data when we do this classification. And in this case, we do have another cluster to compare it with, but it's kind of a teaching example. So that's why. That's why we've got a Y. Did I miss one of the questions? Okay.
I might have just missed you addressing that. Sorry.
That's all right. Yeah, so it's just a way of just finding clusters, k-means, and remember, it's based on the centroid. Here we actually see the centroid get plotted as this diamond with the outline of the same color. And what you'll do in the lab is play with just different numbers of clusters to see how it breaks up that space. And again, remember that the k-means clustering is all it's doing is just looking for how to divide this variable space between petal length and petal width according to these points based on reducing the variability to reach the others. And this kind of concept will be important to remember when we talk about ordination next time for lecture. So there's other ways of getting clusters, and that's hierarchical clustering. And so there's these two types of hierarchical clustering. One is agglomerative, where you start with every observation being in its own group, and then you accumulate the observations as you go up to getting a more and more generalized tree. The other way is divisive, where you start with everything is all in the same group, and then you split it going down. And agglomerative is good for finding maybe many groups in a tree, and divisive is better for finding fewer groups in or fewer clusters with a big tree. And so how do we relate this to the environment? Well, extending from what you guys were doing with working on the species distribution models, I thought it would be good to look at species composition. And this is one of these kind of complicated things to figure out, well, how are sites related? And today, with unsupervised learning clustering techniques, we're going to look at how sites are related based on species within each site. And then next time, we're going to look at how they're related based on the environment that is within each site. And then we're going to combine the two in a plot next time. But today, when we're talking about clustering, we're going to use some of these hierarchical clustering techniques with species composition across these different sites. And this is a kind of a complicated diagram from the reading from this online book, Tree Diversity Analysis. And all it's saying, all these different shapes are supposed to be different species. And then for each site, we have a different count of each of these species. So site A has species 1, 2, and 3, and it's only got one of each. Site B has more species richness. So it's got 1, 2, 3, 4, and 5, and only one of them. Site D, it's got 4 species, and 2 of them have 2 each. So the question is, how would we compare these different sites, and how might we cluster them? And so there's a vast literature on this. And so we're just going to look at some of the most common methods to look at really what's called the ecological distance between these sites. So there's a little d measure here, and we can talk about next about like what are the ways that we can kind of quantify this ecological distance between the site based on the species composition. Okay. And so that might be, we might get these clusters like these 2 sites are really related because they have similar species and similar counts, whereas these sites are more related than those other 2 because they also have similar species and similar counts. Okay, so we could take this cartoon little set of sample sites, and now imagine that we've got these 3 sites, only 3 sites and only 3 species. Well, we could map or plot, I should say, plot that into a Cartesian coordinate system. So we could say for site A, on this axis, we got 1 species. So here's the origin is 0, 0, 0, 0. So that's all 0 here. So site A has 1 species of species 1, and species 2, it has 1 species, and species 3 on the Z axis, it's got 0. So that's why its dot is right there. And then site B, okay, so this is it's got a lot, it's got 5, it's got the most of species 1 and 2, and also 0 of species 3. So it's over here on species 1, species 2. And then site C, it's got 0 of species 1, 0 of species 2, and 1 of species 3. So there are, in the lab, you calculate these things just using, there's this vegan ARC package that it looks at historically like vegetation and different indexes there. And we'll use vegan again next week with the ordination lab. But the simplest are Euclidean or Manhattan distance. So Euclidean is just using Pythagorean theorem. You know, it's the square root of a squared plus b squared, square root of that gives you the hypotenuse. And that's what we calculate this distance C to A, for instance. But then comparatively, the Manhattan distance is a little weird, but it's actually just the computationally simpler because it follows the dimensions. So you go down 1 over 1 over 1. So that would be a 3 from C to A. And this would be the hypotenuse from C to A. So that's why you see the Euclidean distance has this decimal, and the Manhattan distance, it's a whole integer because we have a whole count of each of these things. Now they could be percent cover, could be a decimal value instead of the count of the species, but these are it's like the simplest no-brainer kind of way to compare these different sites based on, let's say, species counts. Okay, but what's more commonly used is this Bray-Curtis dissimilarity. And it's dissimilar because the way the index is set up is a value, it's bound between 0 and 1, and a value of 1 says it's completely dissimilar. Like maybe there's no species in common between the 2 sites, which you can see is the case between site C has 0 species in common with sites A or B. So that is completely dissimilar. So so here sub I sub j, that'd be like you could say CB, B and C, that 1 minus 2, and then this guy. So these components are, it's pretty simple. So C is the sum of the lesser count C for the shared species common to both sites, I and J. Okay, so we don't have any shared species, so that just zeroes out. So it's 1 minus 0, so it's 1. And then this S is the sum of all species counts for the given site I or J. Okay, so if we look at that again, we can then do this across each of the sites. So C to A or B is just 1, completely dissimilar, don't even share any species. Now A and B are similar, so we take the lesser, so 1 versus 5, and here 1 versus 5, so 1 plus 1, that's this C term, so the sum of lesser counts, so 1 plus 1, and then the sum of all species found in each site. So site B has 5 plus 5 is 10, site A has 1 plus 1 is 2, so 2 plus 10, and then we get basically a value of 2/3. So they're dissimilar in their counts, but they're actually identical in their species. And yeah, so there you have it. Okay, so there are a bunch of other metrics for looking at species composition, but this is probably the most commonly used one, and this is what you'll use in the lab. And for the rest of the hierarchical clustering, this hands-on machine learning with R does a pretty good job of kind of describing it. So I'm just going to go over these materials here, and in this case, they're using the aims, so they're using a different data set. We're using, going to use this data set called Dune, not after the movie. So it's not species on a different planet, but it's this dune meadow species in the Netherlands. And so you can get help on the dune data set, and I'm encouraging you to check it out and look at how many rows and columns, what they're composed of. And it's basically different species found in different sites, and then you're doing this comparative thing. So here you're going to just use this that same simple example that we had, and you can calculate using the vegans, veg dist, this Manhattan or Euclidean or Bray-Curtis distance, and you get these distances back. And this is what I was just showing you. And now this you'll do this lab on this Dune data set. And when you calculate that distance, you get this matrix back of correspondence between sites of how between all sites, what's their ecological distance from the other based on the species found within. And then you can do this, you can cluster in a variety of ways. So here's this age cluster. And so the lab is mostly the code to apply to our environmental example. And then I'm saying for each of these sections, see the text accompanying the code. So go to section 21.3, and this goes directly to that section on agglomerative hierarchical clustering. So this has different tips, but it's also using a different data set. In this case, it's the Ames. So Ames, Iowa happens to be a hotbed of statistical researchers. And so they really nerded out on this housing data set. And this, it takes that housing data set and it's trying to cluster based on finding houses with similar properties. And so we're doing the same thing, but we're using environmental data based on species composition for this dunes data set. And here with the agglomerative hierarchical clustering, here they're using Euclidean distance to get the dissimilarity matrix, but you guys are using the Bray-Curtis because it's a better measure of species dissimilarity. So you're going to run these, and then Agnes is the specific method to do this agglomerative clustering. And then you can see the results of this, and then the divisive. So we can look at these results in the lab. And so this is the age cluster, and you should see that the age cluster has this aspect of, even though all these rows are even with each other, it doesn't, and evenly spaced, that's not a reflection of them, you know, how tightly clumped they might be with one another. But you do get that with these other techniques like Agnes. We can look at this, and this is a dendrogram. So a dendrogram is a tree-based plot that describes how related these sites are. So each site is given a number to identify it, and then you see which sites are most related to the other. And that's based on that height of overall dissimilarity here between each other. And so you'll play with different methods of this stuff, and then this also describes how you might not know how many clusters you want from the outset, which you need with k-means, and you can look at how much variation gets explained as you increase the number of clusters. And so the way to understand clusters is that you can break off clusters at any point in this tree. So that determines the number of clusters you get back. And that's visualized here with the Ames data set, which has a lot of individual houses and the properties there. And then you guys are going to do that for the Dune data set, which only has 20 sites, or is it 30 sites? I think it's, yeah, 20 sites and 30 species. And then you can, based on this threshold, that simplifies this tree to 4 clusters. So each of these would be given a different identity and grouped accordingly. So yeah, this is, yeah, just a little kind of brief excursion into clustering. And yeah, this is a really useful technique to know in general, to understand how to get data observations that can be similar to one another. So,
hey Ben,
mhm.
I have a question.
Mhm.
Sorry if you already addressed this, but I'm just kind of wondering, like, what are the implications of like classifying sites in this way? Like, what are real world applications that you would do with that information?
Mm-hmm. Yeah. So let's see, from like a species level.
Well, one thing it does is it it enables you to name the particular type of habitat and get to like a really fine level of habitat definition. So, because you can have like coastal sage scrub, but then your coastal sage scrub is predominantly white sage or chamise or something like that. That's what I'm thinking of.
That's a great example, actually. Yeah, so what are like the ecotones, what are the communities of species that are similar and related to each other? And if you're interested in, say, conservation, you might want to make sure that you preserve the different communities with some, let's say, proportionality, so that there's long-term viability. Now, you can also look at, and this will make more sense when we start talking about ordination, but you might look at like the functional traits within these species and that confer different like larger ecological processes. And really, like unsupervised, we're going to do clustering again with the Google Earth engine, and that is how like a lot of land cover types they look at, well, okay, so this is low, medium, and highly urban environments, or this is, well, water, that's pretty straightforward. But then this is forest and deep or hardwood forest, and then this is maybe like younger growth forest. And so those classes, you might actually say like, well, we've got enough variation in whatever data we're using to interpret them to be able to identify these three classes, and then kind of retrospectively name them according to those properties. So yeah, it's a really good question, and it's kind of like I think it's like a nice step to look at from previously. We were looking at individual species, just one species, and looking at the underlying environment. And now unsupervised learning is like it's kind of a natural segue into looking at clustering, because you might not know how those species are related, but then this is a way of suggesting how they might be co-occurring species, for instance, within sites, and maybe they functionally work well together. So yeah, it's a really good question. And are there other examples that come to mind that anybody else has worked with or thought of or come across? Let me see. I'll pull up also a slide about how is clustering in general used. So I was looking at this. Let's see. This is Andrew Ng's slides from his Coursera, and this was over 4 million people have actually signed up for this class, and this is what he was pointing out, the applications of clustering. So like beyond environmentally specific, this is like market segmentation. So if you want to understand customers as different clusters, but you could also think of this like, well, maybe it's like understanding ecosystem services and which species consume which things, and are we how do we divide up the environmental space, whether it's species or environment or community, into blocks that we can manage. Social network analysis. So this actually is pretty important for understanding relationships between each other. There's actually even there were these seals that they put these cell phones on top of their heads, glued them on their heads, and looked to see who's associating with who. So when they would come in proximity, these cell phones would like register each other, And so they would see that the dynamics of individuals. But this is also like, it gets used in understanding who, if you're implementing a new technology, let's say a sea turtle excluder device, who in the fishing community could be an influencer that could propagate that effectively. Compute clusters, so that's a more obvious clustering, and data analysis with astronomy. So yeah, anyway, it's a very common technique, especially when you're exploring data and you're looking for groups that you want to cluster for management's sake, and doing some follow-on operation. Yeah, but that's a really good question. Okay, another new message. Oh, okay, cool. We got oh yeah, ecoregions. Yeah, we kind of talked about that.
Yeah, sorry, that was like my
Mhm.
question from before. I just went ahead and vocalized it.
Oh yeah, great. Yeah, so marine biogeographic realms and species and endemicity. Okay, Costello. Yeah, I worked with Costello. This is a good one. Yeah, exactly. So this looks a lot like there's a whole bunch of different regionalized approaches to looking at like ecoregions, and this is good. There's like looking at just oceanographic data. There's these Longhurst ecoregions that is also similarly from just a clustering exercise done, and yeah, this is a great example. Yeah, there's a long history of doing this. Oh, and he even he mentions dendrograms. Does he actually show any? Maybe in the supplementary materials. But yeah. Yeah, that's a good one. Yeah, so I think that's what I've got for now, and then I can I'm gonna kick around here to answer questions and also like revisit the great questions in the Slack that you guys had on the last lab, and I really need to start filling out stuff. Got a wedding to go to shortly, but so I can't extend the time too much, but yeah, I'll kick around and we'll just leave this open. So I need to install packages on Taylor. So I'm going to do that in the background too. But feel free to chime in with other questions or comments while I get this loaded. Oh yeah. So yeah, I can go through those questions. Let me just start this. I think I'm just going to take the little shortcut. Let's see. Let me just get this. Oh, whoops. Wrong one. And then I can go through those questions once I get going here. And that should install things too, for everybody. Okay, yeah, let's. I went over some of these questions in the office hours, so I can at least talk through them and with you guys here now. So feel free to tune out if you're already in the office hours, or if you just want to, get working on the lab. But maybe it would be great if I don't know if you guys want to specifically say which ones you want me to focus on to start. Might help a little bit.
I had a question in the Slack about
Mhm,
when you're initially cleaning the data for lab one
mhm,
and
mhm.
or for any data set really, how do you know if two or more points with the same exact coordinates was recorded as two individuals or if it was like perhaps a duplicated point? I
Mm,
may have addressed something
mhm,
similar to this like pretty early on, but I was wondering if you could elaborate on that and like how you would
mm,
look at the metadata to determine if that was likely.
mhm. Yeah. Now, do you have, excuse me, a lot of duplicated data in your data set by chance, Juliet? Did you?
I had a fair amount of duplicates, and some
Mhm,
points were curious because there was like 4 duplicates of the same exact coordinates, but they had 4 unique keys. So
mhm,
especially because my species is like gregarious, I was wondering if someone in the field took one coordinate, recorded 5 individuals in one burrow. And
mm,
so it is partially because my species is probably likely to be closely clustered, but I think this could apply to a lot of species.
mhm. Yeah. So, it's interesting. We're you're pulling from the Global Biodiversity Information Facility, is GBIF is what it's called, and this originally was set up as a way for museums to share specimen data. So specimens are what museums are particularly interested in preserving in order to identify individual species. And so originally it was set up to exchange information about who has which specimens on which species. And that was called like Z.50 or something a while back in early internet days. And now it's increasingly been to share observational data. And the observational data is based on this thing called Darwin Core. And this is a standard to share species information. And it has a bunch of terms in it. And so this underlies a lot of the actual GBIF record and some of the fields that you're seeing. So basis of record, is it a preserved specimen, fossil specimen, event, human observation, machine observation, taxon occurrence, material? And then there's also like the data set. Where does it come from? Where's the institution? And it's possible, for instance, that the same observation could have been made and shared then between multiple institutions. So one surefire thing would be to look at, well, what is the date observed? And is that the date of observation, is that unique in time? Does it, a lot of times it will only have a year. Sometimes it won't have a year and it'll just have a day or a month. So the data quality can be kind of hit and miss. But this is like the authoritative reference for how that data is supposed to be stored and shared. And GBIF is actually this federated system. So there are a bunch of different nodes that feed into GBIF. So for instance, when I started working on this stuff back in 2002, oh my God, 20 years ago almost, at Duke, it was to set up this marine mammal, seabird, and sea turtle global observation data set. And that was OBIS-CMAP based at Duke. And then that was a node that fed into OBIS, the Ocean Biogeographic Information System. And then OBIS feeds into GBIF. And so there is this possibility of duplication between records. The other thing that's kind of interesting is that some of these could be the same individual, but then let's say it's some telemetry data set. So you're tracking the individual through time. And in that case, you might get a real oversampling effect. But there is a way to tease that out based on, again, the basis of record. And there's this other thing called an event core that you can also have a series of observations associated with a given species. So let's see, it'd be better to actually crack open some duplicates with the data you got, and then we could even look at that. That's just like the biggest hand wavy kind of stuff. So I can put these, I'll put these links. So let's see, for instance, Julia, what's your species?
A black-footed ferret.
Black-footed. Oops. Okay, data sets, species. Nigripus, Pretorius, this guy? Or no, this guy, Mustela.
I think it's the Mustela nigripus one.
Mm-hmm. Okay, so cool. And it's endangered. And at some point, there's a way to look at the actual 803 occurrences. Okay. And so here we've got, maybe I'll just, if any of these pop out as being, well, see, like there is this other way of, even here, we could look at the basis of record. So human observation, preserved specimen, unknown, interesting. You see the numbers there, coordination uncertainty. Different
Cool,
months.
thank you. I can check this out later as well if other people have questions.
And then some others also mentioned issues and flags. So this is actually kind of a newer GBIF feature, all these different flags that they have. Continent invalid, recorded date invalid. This would be another way to filter out stuff that might be spurious, where there's potential issues. Yeah, cool. That's a good question. So I'll add this here. I wonder if this will work. Any other questions to address here?
Yeah, I had one in the chat actually, just along the lines of the duplicates, is how deep are we expected to dive into duplicates for the lab? Like, is that something we should really spend time on, or should we mostly focus on generating and understanding the maps and predictions?
Yeah, I mean, I think the lat long, it's probably good to just remove the duplicate so you don't get oversampling on the same environment underlying it. But I think, yeah, the main purpose of the lab is just to give you exposure to some of the modeling techniques, and the data cleaning stuff can go on ad nauseum. So I would say, yeah, hopefully just removing some of the obvious duplicates that are in space would be the most, with latitude longitude duplicated would be the simplest kind of filter. Yeah. Okay. Yeah, the duplicated obs key. Okay. Yep. The GG ally plots. So this I talked about also in the office hours, which, I mean, obviously only some of you were at, but let me go back to that. So I think that was with this regress. So this is unnecessarily complicated because, well, what I like about it is, let me show you the simpler version. Oh, oops. This one. This is the simpler version that conveys sufficient amount of information. But let me just compare the two and talk about this a little bit more. Okay. So really a pairs plot, which is what this is, what the pairs part just means that it's doing a pairwise comparison. In this case of our, for this plot of our each environmental predictor, our X, and what we're trying to fit. And see, when you take all the predictors, X's, you can have them as the names for the columns, and you can have them as the names for the rows. And because of that, it's going to show up twice, each combination, whether it's like here, altitude and bio1 show up in this lower triangle as a scatter plot. And in the upper triangle, we see the correlation coefficient. So that's just a bit of real estate to look at these pairwise plots and to be able to do like two different things that describe the combination of variables. And really, this GG ally pairs plot, the point of it, or this simplified pairs plot, the point of it is to look for autocorrelation and to look at the distribution of our data on the diagonal. So this is really made up of a diagonal, which is the variable itself. So it's just, that with itself, and you only get one combination of that. And then with every other variable, which you get two of, and on the lower triangle, you get a scatter plot. and in the upper triangle, you get a correlation coefficient. And so you can see with this altitude in bio 1 that this is really tightly, it's a tight relationship. And that's why you have a 0.92. And then the numbers get smaller in this as the correlation coefficient gets smaller. Now, and then on the diagonal, you see that some of these variables are not like normally distributed. And generally, a lot of regression techniques, they do a better job fitting the data when there's like a normal distribution on your predictor. So you might transform some of the inputs, like stuff that is really skewed on the low value end, like this ER try. You might actually do a log transform, and then your GLM and GAMs might perform a little bit better. But we didn't really get into that. That's another thing you might look for. Now, this GG ally, what I liked about this is that it did show me not only the distribution of the valuable variables, but I could do this, I could color the aesthetic according to that presence, the response term. And then that was similar to that original explore graph that I had down here at the bottom. So that's similar to this, which is really what our model is what we're trying to get it to do is differentiate between the presence coded as 1 versus the absence coded as 0 in gray. And so that's what our different modeling techniques are trying to do, is understand this environmental relationship. Where does this critter live, and how is it differentiated from the background or pseudo absence points that we generated? And that was the tail end of this first lab of exploring. Now, with this GG ally, if we just would have added some transparency, it would have been easier to see that this diagonal plot that it by default has is basically the same thing. And that's particularly what I liked about it. But what I don't like about it is that it's got all these other correlation coefficients that are specific to just the presence or just the absence, whereas really we only care about the correlation of each predictor to itself, and so this just overcomplicates it. So I'm sure there's a way to tune that. So we look at just the correlation coefficient for all points. And really the point was that we can look at that to address some of that multi-collinearity in model selection to reduce the number of variables that might be autocorrelated with each other when we do the model fitting. So yeah, and then we ended up doing the VIF and other things. So what's good is just to understand the scatter plot, see that relationship, and then look at that correlation coefficient between the two variables. I think this just simplifies things immensely. This is the default from the environmental stack that we fed in, and it doesn't actually have the latitude and longitude in it, and it doesn't have the response variable in it. So could be added, but yeah, that's some of the differences there. And apologies, we're kind of exploring it, and like those are three very similar sets of figures that kind of overlap with each other. But hopefully seeing them in these slightly different contexts kind of gives you an idea of why they're relevant, and which parts are useful versus not. Okay. let's see. Yeah, so yeah, the numbers, these are, you know, that's just the zeros and just the ones, but we're not really interested in looking at just the correlation of just the zeros or just the ones. It's the overall autocorrelation between the two variables. So the gray correlation coefficients are more relevant. And yeah, I'll have the lab submission guidelines up tomorrow, promise. And yeah, it's not meant to be a super hard lab. I just want to, I know that there's been a lot of, you know, confusion about these concepts. There's a lot here going on between, you know, splitting and fitting and predicting and evaluating. And I really also want to get this a little Shiny app going so that you can see more complicated stuff, like with evaluating. Actually, I have it in the lecture. Like this would be, I'm hoping to get this up tomorrow. Oops. Let me show you what I'm going to try to do. See, like the confusion matrix, well, it's confusing. So like, wouldn't it be cool if you could just like change that threshold value and then see how the habitat grows and shrinks, and then with that little matrix of presence versus absence, see how that changes as you basically tune your dial. This receiver operator characteristic curve, it was actually developed, I think, in World War II to dial radios, and it was, and you're looking for the signal to noise, the sensitivity versus specificity, and really we're tuning the dial, and so these are important concepts that the more that you can play with them and see how it changes the outputs, that the more I think it'll make sense too.
Ben, I have a question.
Mm-hmm.
For the GG ally plot that you had before with the two different colors for presence and absence, and so I understand that we'll focus on the, like it's an autocorrelation and we focus on the gray value.
Mm-hmm. Mm-hmm.
What does it mean if it's high or low? Like what does it mean? Can you remind us which ones we like, what's meaningful or what's not meaningful about the high and low values? Thanks.
Yeah, sorry, I didn't mention that. Yeah, so if we go back to the GG ally, or actually, I'll just, there's actually a difference here between these values. So you'll notice that this one, this is simplified and they're only positive values. So this is like the absolute correlation, but the correlation coefficient can also tell you the direction of that signal. So in this case, the correlation coefficient is negative. As we increase in altitude, the bio1 values go down. So as x cruises along, bio1 values go, and that's why that's negative. But you notice that over here, it's still the same direction between altitude and bio1, but this is just a positive value. So this is the absolute value. And really, we only, when we're looking at autocorrelation, like one rule of thumb, and this is what you guys actually use for in the lab to for the threshold, is a correlation of anything greater than 0.7 is considered autocorrelated with another predictor, and this is what is getting removed. Now, which predictors you remove, that can also vary a lot too. So let's say, and this is what discussion we had during office hours was, you know, if altitude is really important based on, let's say, the literature and how you might want to conduct field surveys, and where you can do survey design and all that, then maybe you keep that one in, even though it's the most autocorrelated according to this VIF value being the highest with all the other variables, and it has the highest correlation coefficient. So maybe we drop bio 1. So when you're doing the model selection, you can also be explicit about the variables you want to keep in, and then try evaluating the model with some of those dropped out, and then in the end you can actually fit the model and look at this AIC value for the GLM and GAM type of models, and the lower the AIC, the more parsimonious the model. So that the model selection, there's actually a lot of different ways, and I was hoping to show some more examples of how you might be more surgical and manual with it. But the basic is just looking for these autocorrelation values, and a general rule is 0.7 or 0.8 or higher is considered really autocorrelated. And if and so you might remove that so you don't misinterpret the relationship between the environment and your response, meaning the presence or absence of your species. Yeah.
Cool, thank you.
Mm-hmm. Okay, so this should be all the packages should be installed on Taylor, and I say keep on using Taylor too, because it's really awesome that I can actually jump in and try running your code in your same environment and see any errors and stuff that you guys have. Yeah.
I have a question.
Mhm.
I still am having a little bit of trouble with Taylor and getting an error right at the beginning. I don't, want to take class time figuring out my code, but is there a time that you could maybe look at it?
Yeah, we can look at that. I mean, if nobody else has questions, then we could do that right now. Yeah. Sorry, who is that speaking?
It's Grace.
Grace, right.
Sorry, I don't have my camera on right now.
No, that's okay. Yeah.
I hope it's just a really small fix. Maybe let me just share the screen and then just, if that's okay, hopefully.
Yeah.
Like 5
Yeah,
seconds.
go for it. Go for it.
Oh, you've disabled participant screen sharing.
Mm-hmm. Let me get that going. Okay, go ahead and try again, Grace.
Okay, cool. Let's see here. All right, you see that? This is the error that I'm getting. And I did that lib pass. I don't know if we still need to do that now that you have the like.
Oh yeah, let's not do that. Where do you have the lib pass set up?
I did it in the console before, and so I just checked it now. To be honest, I'm not exactly sure how this all works. So.
Yeah. Okay. So let me just back up for a second with what was going on with that lib pass. So originally, I was trying to speed up your ability to run the labs by trying to give you the path to where I had previously installed some of the packages. And that was before I had administrative privileges on Taylor to be able to directly install the packages. So what the libpath does is this is where R looks for where our packages are installed. And it does it in this, I think it should do it in this order. But let's just let's try this, Grace. Let's
Yeah.
not deal with setting the live paths
Yeah.
and just go up to
how
the session menu.
How do, okay, okay.
And you see the session, not that one, sorry, the
Yeah.
other, the one to the left
Oh,
inside RStudio. And let's just restart R and clear output, sure.
cool.
And then why don't you go ahead and try to run, you can select lines 13 through 20 again.
Oh my goodness, look at that. No.
No. Ah,
Does that clear the lib paths? Does that remove it? Should I check it again?
it's weird. Because
Okay, yeah, it did remove those. That's good, right?
but yeah, I guess you might have an old version of raster, but you know what, let's try this, because in the main library, I think it's the newer version of raster. So let's
Maybe.
just uninstall your version of raster. So if you go on to the packages pane in the
Wait.
lower right quadrant.
Would it help if I like quit this session or something and like reopened it? I haven't quite done that yet.
Well, we did that with the session, but
Oh,
what I
cool.
would suggest you try is that I think what's happening is, like, I think you might have an older version of the raster package installed in your library.
Gotcha.
But if we basically just uninstall that package from your library, then I think it'll use the system library, which has a newer version of R.
Okay, how do I do that?
So let's see. I think I'm not sure. I think if you detach it, so if you go up to the packages pane on the lower right quadrant, yeah, and then type raster in the search. Okay, so this is interesting. See this? You've got two versions of raster. So why don't you click the X next to 3.4 version to remove that? And so wait, just so we're understanding this, so see that tilde? That tilde is actually referring to your user folder. So that is equivalent to that first live path. And so what we're doing is uninstalling from your user library. And let's say yes.
Oh, okay. So this isn't for like, this is just, so we have like a user library of packages and then like a whole Taylor library of packages?
Exactly. So that's what those two paths are. One is, the first one is your user library. So you can go ahead and say yes to that.
Okay.
And the first path is your library, where you have the ability to write new packages that you want to install into. But because it's the first path, it's going to default to using whatever library is in there before loading the system library that's in that second path.
Oh,
So now
now
we just removed that one from your path. So if you run line 18 and 19 again, see, this is a different actual error.
Yeah.
Cannot be unloaded. So in that case, let's go to that session menu again and just restart, clear output. And now let's try running that chunk one more time. And we're back from outer space.
Yay! Oh yeah, I knew it was gonna be a small fix, but one that would take me way longer to figure out. Cool.
Yeah. So that was just a funky chicken.
Now we can get back. Now we can get on to Taylor. Fabulous. All right. Well, all night. Cool. Yeah. Awesome.
Great. So now you know, like, where those paths are located, and then that was really interesting to see those two different versions actually in the packages folder. So it recognized both of them, but just showed, yeah. So you could easily uninstall, which is great. Cool.
Cool. Well, thank you. Yeah. Cool. Cool. I will stop sharing. I think everybody else has left. And awesome.
Cool. All right.
Thanks.
I'll see y'all later.
See ya.
Cheers.
Bye.